I thought as a primer to this distinguished lecture, I'd like to share some insightful quotes from the man that this medal and lecture are named after, Dr. H. Bolton Seed. So here are a few things that I was able to come up with. Always know what range the answer should be in before you begin. That's pretty good practice, I think. You will get a better job by letting the experts do their job without political or financial pressures interfering. That's quite interesting, isn't it? Because we're driven by financial pressures especially, but I've also done some engineering by politics in the past too. In regards to discovering geologic hazards, it is interesting what they find when they know what they're looking for. Get the facts first, the theory later, then you will have something to check the theory on. I think that's some pretty wise advice. Another one, the job of the engineer is to judge whether the computer output is right or not. It can and does come out wrong. One should know the magnitude of the expected answer. And here are a couple other ones, the last two I think I particularly like. He says, don't work for poor clients. They can seldom afford to do things right. And then the last one I really like. A lot of experts, and he quotes experts, a lot of experts will say almost anything for $500. Well, it's my pleasure to participate in the Seed Lecture that is given annually by the recipient of the H. Bolton Seed Medal for outstanding contributions to teaching, research, or practice in geotechnical engineering. This year's winner of the H. Bolton Seed Medal is Dr. Norbert Morgenstern. Our speaker was a past Terzaghi lecturer in 1992. He is well deserving of the medal. Dr. Morgenstern is currently a distinguished university professor emeritus of civil and environmental engineering at the University of Alberta. He has authored over 300 research publications which concentrate on geotechnical aspects of oil sand development, permafrost engineering, dams, mine waste management, numerical modeling of geotechnical structures, progressive ground failure, landslides, and risk analysis. His research has made a significant contribution to the practice of geotechnical engineering worldwide. Dr. Morgenstern is widely recognized as one of the world's preeminent civil engineers. His research deals with the failure and flow behavior of waste dumps, tailings dams, and other granular structures, an issue of considerable importance to the international mining industry. Research conducted under the direction of Dr. Morgenstern has shown that static liquefaction is an important factor in triggering flow slides of these large dumps. New theoretical developments provide the basis for assessing the initiation of instability and the flow behavior of these enormous earth structures. Dr. Morgenstern's current work also includes research on the development of probabilistic methods of slope stability analysis and their calibration with reported case histories, and additionally the development of risk analysis procedures for landslide assessment. He has been the recipient of over 40 prestigious honors and awards. Now I'd like to ask Dr. Morgenstern to join me here at the podium, please. Dr. Morgenstern, in recognition of your contributions to the state of practice of geotechnical engineering through research as a professor and consultant, I would like to present you with this medal. I very much look forward to your lecture on risk and reward, geotechnical engineering of the Alberta oil sands. Thank you for your leadership in our profession. Thank you.
Thank you very much for your generous introduction. I want to thank the Geo-Institute for this wonderful award. I had the pleasure to have known Harry Seed and to have worked with him on occasion. He was an inspiring teacher, dynamic and creative researcher, as well as a wise and much valued consultant. So it's a profound honor to receive the medal in his name and enjoy the list of illustrious colleagues who've been selected for this award in the past. Turning to my lecture, this lecture, perhaps by intent, but certainly in my case, is intended to be awarded to someone towards the end of their career, not the beginning. Therefore, I thought it would be of interest to share with you the involvement over several decades of geotechnical engineering in one of the great industrial undertakings of our time, and thereby, at least by inference, to illustrate the three dimensions of Professor Seed's career, which is celebrated in this medal and in this lecture. That is, the role of education, the role of research, and the role of professional practice. Let me turn firstly to the Alberta oil sands as they are and talk about them as a resource. This slide illustrates the current reserve situation of the oil sands, but as a resource as opposed to reserve, they constitute some 2 trillion barrels of bitumen, which, if recoverable, could satisfy North American oil demand for several generations. However, the current reserves, which are defined as that which can be recovered with current technology, are some 77 billion barrels, making this reserve second only to the reserve of Saudi Arabia in terms of recoverable oil. This is an amount that could go into reserves with additional new technology. Of the total reserves, the approximately 20% of the volume is recoverable by mining, and the subsequent 80% is recoverable by in situ techniques. The reserves are located in the northeastern corner of the province of Alberta in Canada, and the outline, the mottling, I'm afraid doesn't show up clearly enough for the room this size, illustrates, if you like, the subcrop of all of the bituminous deposits. It's very extensive. But the area that is mineable is this which is surrounded by a boulder outline. This illustrates the mineable area, or at least part of it, and it surrounds the Athabasca River, which runs through the terrain, and we'll see locations that will comment on Suncor and Syncrude and Shell and other operators. These are all surface mining operations, or about to be, going a little further north. As we move out further to the east, we get into some underground operations, and further south and further to the west, also underground operations. Looking at the terrain from satellite, we see lots of mining operations, and we see lots of terrain in which much of the waste is being managed, indicating the substantial problems of dealing with tailings and related matters. This is a little further north than the one I just showed, showing new developments. This is now in commercial production. There's a new project being developed by Exxon over here. Very substantial undertakings in which we have lots of open pit mining, we have lots of tailings dams, we have a number of other geotechnical challenges dealing with that. At this time, approximately 50% of commercial production is produced through the mining endeavors that we'll be talking about. The other 50% is produced by in situ injections of steam technology we won't talk about, in which the geotechnical issues are by no means zero, but are subordinate to the problems of mining, the mining-related endeavors, except for the hydrogeological considerations. They're very substantial in getting the water to create steam to stimulate the underground the underground reserve. At this instant, the spend rate in the industry is about $15 billion per year in terms of capital investment, and a comparable, perhaps 10 to 12 billion a year in terms of operating. At this instant, we anticipate the production to rise from about the 1.5 million or a little more of barrels per day produced through this technology to about 3 million barrels a day by the year 2020. And if we multiply that nominally by days per year, that's about a billion barrels a year. And if we take a nominal price of oil, which even today is $100 a barrel, and will presumably be somewhat more by that time, that's a revenue of $100 billion a year, which means we've moved out, if you will, from the experimental phase of development. So this is a very substantial industry that has been maturing very effectively and is maturing very quickly with lots of technical challenges, both in terms of production, in terms of environmental matters, which we'll chat about as I go through this presentation, and in which geotechnical engineering, I hope you'll feel some pride at the end of the presentation, has been central in the successful evolution of this major undertaking. Just by illustration, this is a cross-section through the deposits, which illustrates the source of the hydrocarbons which migrated upslope, but we won't talk about that. This illustrates the Rocky Mountains. This is the region around the central community there, Fort McMurray, and the oil sand deposit it lies, if you like, at the top of that inward and upward flow of hydrocarbons many millions of years ago. We think the best explanation is that bacterial action chewed up all the light ends, leaving a deposit that does not flow and hence is obtained either by energy stimulation at depth or by mining and energy stimulation in a plant. The other aspect of this section is to illustrate that part of the deposits are very close to the surface. Indeed, we'll see some are at the surface, and that's the area in which the mining is taking place. Clearly, it's a stripping ratio that dictates the commercial activities for mining. When that becomes excessive, one has to go in situ. This, in brief, shows the flow chart for a mining operation. One mines, the current mining technology is a truck and shovel. We'll discuss that evolution in due course. Then the material is crushed on site, sent by conveyor where hot water is added and agitated, and then this is all slurry hydrotransport into the plant, into particle separation vessels, in which the bitumen froth is extracted and processed in a kind of refinery activity, and then we have a very substantial amount of tailings to be managed, both under operating conditions and for reclamation and closure in due course. The deposit began its development in the late 50s to the later 60s, and if you were undertaking site exploration studies in the early 60s, this is the kind of idyllic conditions that you might be undertaking, wandering about, looking at exposures. These days, it's more the roar of 400-ton mining trucks that pervade the environment as opposed to those days. But when some of our distinguished colleagues, for example, Ralph Peck, visited the area to look at slopes in the 60s, while he didn't necessarily go out in the red canoe, he would have seen conditions like this, where the material is an outcrop. One have had some comfort from looking at the outcrops that yes, this material, which is not cemented, it's very friable, does stand effectively in natural slopes, though clearly they weather. As one continued around, one would see that the material spalls, and one would find, particularly when hot weather gets on this bituminous sand. It spalls very rapidly. One can also see sometimes traces of bubbling going on. But these are the kinds of observations one would have made in the 60s. There were thoughts in those days that if this were ever developed, you couldn't leave a bulldozer, a tractor running on this material because it would actually sort of liquefy it and soak into these soft sands that sometimes flowed related to these gas conditions. That's an amusing contrast to know that we're now running 400-ton trucks quite happily on these materials, but it shows you how far we've come in understanding. This is an early set of geotechnical information that had an enormous impact. The actual tests were conducted by Elmer Brooker, who's an old colleague of some friends here in the audience when he was at the University of Illinois many years ago. Was a predecessor of mine, the University of Alberta, and the founder of EBA, Elmer Brooker and Associates Consulting. But the important technical point is that it shows unconfined compressive strength of samples with depth. Depth is the ordinate, and one sees that the strength of these materials is decreasing with depth, giving a sense of problems when you begin to explore these materials, develop the materials. So this data, which was obtained with a pressure core barrel, and the samples were then frozen, and the samples were then taken into the laboratory and thawed and compressed, were certainly for the middle 60s best available technology for characterizing the deposit. And the information said there is trouble once you get away from the stronger surficial deposit, which led to many of the suspicions that the material behaved poorly as one tried to develop it. I think, fortunately, there was the desire to test these conditions under fuller scale, and large-scale test pits were undertaken. In this case, a scraper test pit in 1964 gave considerable comfort that this material was going to be mineable by one technology or another, and that was a pivotal learning to advance the technology. Nevertheless, as one mined and one saw, say, in pools or other things, one kept seeing the pervasive aspect of gas bubbling under these locations, and the question remained, certainly there have been gas effects affecting geotechnical behavior, and will gas be an issue? In the middle 60s, there were two consortia, one called the City Service Consortia, which morphed into Syncrude Canada Limited in time, and the other called Great Canadian Oil Sands, which was a subsidiary of Sunoco, Sun Oil Company, which morphed into the company now called Suncor. And I'll use their more modern names, but there were corporate evolutions, of course, in all of that. So Suncor, in fact, was the first to choose to go commercial and the first to get a permit to do that. That made the City Service Consortium sit back. Those days, oil was something like $2 a barrel, and so this was very much a risk capital undertaking. So Suncor then proceeded to develop a design. In the middle 60s, the original estimate for getting into the business was about $190 million as a capital investment, and by the time they spent their money, it cost $250 million, which was a significant amount of money for a new technology, certainly at that time. Did this pay off? Well, the current Suncor market capitalization is $65 billion. So they did something right along the way, but when I arrived in Alberta shortly after they were in operation, the recurrent claim was, can they stay in business? There were so many problems, and they were losing money. So certainly commercially, we see one measure of risk and reward in the very successful transformation of that sort of roll of the dice by this corporation converting into what in Canada is one of our corporate leaders. But technically, what did they do that is of interest to us? They began with bucket wheel excavation, following the kind of technology that was common in the German coal mining practice. And there were a number of issues related to that. There were cold weather workings. I should add that it's not uncommon in January to be operating in this environment down to minus 35 degrees Celsius or so. So that's certainly an issue for maintaining production and we'll come back to some of that later on. There were metallurgical problems associated with the teeth on the bucket wheels. There are issues of trafficability because of aquifers bleeding water into the base of the pit. But all of them resolved in the fullness of evolution. What was the more particular challenge that was very geotechnical in nature was the tailings management. This is the plan of the original tailings design and is the only document that I can find going back to the conditions as they started up in April 1967. The design said we're going to take the sand tailings, the sand come out of the processing, and we're going to deposit them over this escarpment. There's an escarpment here. And they're going to flow down, and we're going to have a collection bund, so to speak, a dike. In this case, is going to be 12 meters or 40 feet high. And the sand is going to form an 8% slope, as it might say in a coarse sand operation in a copper mine. And clean water is going to flow out of here, and this water is going to be recycled back to the process. And within about 3 years, there would be enough real estate created in pit to move this waste management back into the pit and not keep it here on the banks of this major river, the Athabasca River, in which you saw the canoe paddling around. Now, I haven't found the origin of that technology, but it obviously must have come from some kind of small-scale experiments of processing by the process engineers, is the only way I can logically interpret where this design came from. But that's not what happened. As the tailings were deposited over here, firstly, they didn't keep an 8% slope. They went a lot flatter. And secondly, what should have been clean, useful water was not clean, useful water. In fact, it had an extraordinary amount of fines that we'll talk about and wasn't recyclable at all. So now you're stuck with a $250 million investment, and it requires maintaining waste management, and you've got nowhere else to go. There's no other location. You can't abandon this. And it was to the genius of the late Bob Hardy, who was Dean of Engineering at the University of Alberta in those days. His company ultimately morphed into AMEC, that innovations were created to resolve this tailings problem. Here you see the only photograph I can find of that time of sand being deposited, fluids being stored here, and this little dike, which was built in part over some 40 feet of normally consolidated alluvial clays and elsewhere in part on muskeg, now having to do a lot more service than was planned. They learned how to build this structure. There was no significant tills around. There were no other construction materials to bail them out. And the decision was made to learn how to build a containment structure with sand, which was the only available material, the sand emerging from the tailings itself. We'll see that they had to encounter a number of construction issues of liquefaction during the early days. By the way, earthquakes here are fairly benign. Liquefaction issues are ones related to static liquefaction. And they had to learn how to build with sand, to maintain drainage, to do their best to keep the fluids out of the river, and stay ahead, of course, of the ever advancing fluids. This structure ended up 92 meters high, some 300 feet high. It's several kilometers, a few miles long. And as I say, partly on normally consolidated clay. I think that if many of us have been asked in the late 60s, can I build a 300-meter high structure relatively quickly on normally consolidated clay, we would have been intimidated by that challenge. But it was built safely with ultimately some challenges of making sure it wasn't built too quickly. And the cross-section that emerged was like this. So this was sand that was placed. This is the original starter dike, and then one built sand beaches and then deposited the sand and then developed containment in behind. We'll see later on when we look at some of the liquefaction issues of building the sand too quickly that they then learned that they had to do what we call now compacted cell to avoid liquefaction and to make sure that we stepped over on material that was dilatant and not contractant, which remains an important challenge in our current technology. So the contributions of the late Dean Hardy, Arthur Casagrande advised him on many issues at the time, addressed this tailings issue in real time, so to speak, and I suppose one can speculate that perhaps had there not been a geotechnical solution to the tailings storage at that time, the development of that industry would have been seriously delayed. There is the structure as it was reaching completion in terms of containment, and we'll come back to that when we talk about the contents of this material, which is a clay slurry that defies some of the laws of soil mechanics, and we'll see it in a reclaimed state in due course. The next commercial stage of next stage of commercialization was the development of the Syncrude project, which began studies in the 1960s. In 1969, it got approval to proceed and began in 1973 with an estimated cost of $1 billion, which ultimately came in at $2.3 billion. Those of you who remember the 70s, remember we went through an inflation stage with one of the first energy crises at that time, and that certainly affected the the capital cost of the project. And by July 30, 1978, the first barrel was shipped. And this corporation also now has a current capitalization of, or if you add up the shares by the owners and so on, which are publicly traded, of some $70 billion. So again, the commercialization has had an economic return in due course. It didn't come easily. This was the initial mining scheme that was presented by the designers for the project, the EPCM, who were selected to develop all phases of the design. And basically they said, we're going to continue. You can see the bucket wheel excavators, the pit here that is deeper than the one you saw in the photographs. We're going to have 2 stages of bucket wheel excavation, going to conveyors and trucks, and ultimately going back to processing. The Syncrude staff at that time thought that there were so many problems of breakdown and limited productivity associated with bucket wheels that they favored a dragline mining scheme that we see here, in which one would have drag lines moving overburden, and then we would have drag lines sitting on top of a high wall, putting reject material that wasn't ore here, putting ore in stockpiles, and then there would be reclaimers sending the material on conveyors to the processing facility. This was a major departure. It was a departure that was fought against by the senior consulting organization. And Syncrude then formed the Geotechnical Review Board, which is still in existence today. Involved the late Dean Hardy, it involved Dr. Arthur and Leo Casagrande and a number of other people, Carl Taylor from Bechtel and others, and I guess at that time was the youngest of the review board. I'm now the oldest. And we did a number of things. We flew around, certainly North America and elsewhere, looking at drag lines. We looked at geotechnical issues. We looked at a major trial excavation with a small drag line and all the things that you might do to come to a conclusion. And ultimately, we supported the view of the Syncrude senior staff that thought the drag lines would have greater cutting capacity, would have better selectivity than the bucket wheels, and agreed that notwithstanding the obviously greater geotechnical sensitivities to this, which we'll come to in a moment, that this was the right way to go. And I remember the day in which we finalized that recommendation, and there was a wonderful man, a fellow called Herman Knight, who I think at that time was president of Consolidated Coal or something like that. And he sat back and said, you know, if we're going to proceed putting machines and men at that risk, we better reflect on the risk. This was this was perhaps my first risk analysis. And he said, if Syncrude makes this choice, they should reckon on losing one of these machines. They're going to have 4 machines working, losing one of these machines every 10 years. And that observation struck a responsive chord. It wasn't a total failure modes effects analysis. It wasn't a quantitative risk analysis, but it was a judgment from a very experienced senior miner with lots of dragline experience, recognizing the adventure that we were going to go into. And that was the recommendation that we made to Syncrude, that part of your business plan, that you must accept the implications of losing 1/4. They're going to have 4 machines working, 1/4 of your capacity every 10 years, and the implications of what that might mean for safety and the like. Clearly, this was going to proceed with the full power of the observational method and other geotechnical matters. So the drag lines were chosen, and here you see the mining. The mine has 2 sides. So the mining goes in a north-south direction, and it has one side in which you see 2 machines working, and the other side is over here somewhere in which another 2 machines are working. Waste is deposited into the pit, or here is put on in these ore piles, which are then reclaimed onto conveyors back into the processing that we saw in the cartoon earlier. Clearly, instability of this is a significant issue. And later on, we're going to see some aspects of trying to construct major earth structures over mine waste as another challenge. So drag lines were selected, and it was important now to understand, in order to have partly in support of that decision, but partly in fixing, if you will, the observational programs, to understand the potential failure modes that might plague this operation. First of all, what was the nature of this sand? You saw it standing up fairly steeply. If you take a sample of this oil sand and test it under conventional manners, you'll get the behavior of an uncemented, dense sand with friction values in the range of 38 degrees, 40 degrees. But clearly, it's behaving a lot better in place than in the natural slopes, and certainly the drag lines were designed to stand on slopes up to 60 degrees. At that behavior that you'd get from conventional geotechnical testing would not have supported the conclusion we came to. We learned how to sample, partly related to research at the University of Alberta. We learned how to sample this material in locations where the same sand of the same Cretaceous age had not been affected by bitumen. These were areas that were barren. When the bitumen intruded, the oil intruded, there were perhaps shales that inhibited the intrusion of bitumen, and we could collect the sand without the presence of bitumen. In the bitumen, gas is in solution, and when you take samples in a conventional way, the gas comes out of solution, disrupts the fabric, and leads to low strengths, which accounted for those low compressive strengths that we saw in the early 60s. So when we got undisturbed behavior of this sand, we saw this interlocked fabric of the sand particles. Casagrande told me that he and Terzaghi were interested in the late 30s, in fact. They knew that if you left sand under load for a very long time, something happens to it. They had experience, perhaps, the St. Peter Sandstone in Minneapolis. I can't remember the case histories. And they tried to actually simulate what happens to it in experiments, I think at Harvard, but the length of the experiments is a function of the patience of a PhD student, and it took millions of years for this to occur, and none of our PhD students have that kind of patience. So it was the need to sample this material, and we saw it's the architecture of the grains. You can see they're embedded in each other. They're not cemented. This is perhaps at best a juvenile sandstone. There's very little cementation, if any, but it is denser than 100% relative density, and is that interlock that provides the strength. So we had some understanding now for going forward that this material, if you don't mess with it, was going to provide adequate stability for the draglines. However, the depositional environment required other reflection. This is a fluvial estuarine environment, and you can find channels being deposited and then channels being excavated and so on and so forth, with the intermixing of the fluvial and estuarine processes. And every time you get a channel like this, you'll get a clay drape often sitting on the side, if any of you have looked at deltaic deposition and studied the facies under those conditions. So if you take, for example, a boring here and then another boring here, it's very difficult to establish stratigraphy. It's very hard. You can do zonation, you can do facies characterization, but it's very hard to do geotechnical engineering based on the simple models of sample, observe, and establish stratigraphy. So that led first then to the understanding that, well, we've got a pretty strong sand matrix if the gas doesn't affect it. But what about these clay drapes? So one could imagine, for example, we're sitting with a machine on the dragline mining bench excavating here, and we've got a clay surface here because of those clay drapes, and we can have block slides developing. But typically, when we went into production, the high walls were typically 50 degrees, not the 35, 38 degrees that you might tolerate on sand alone. One of the big breakthroughs technically was to make use of what the geophysicists had developed for oil well control, which is the dip meter. And originally, when we'd call them to come and do dip meters on our holes, they would say, "How deep is your well?" And we'd say, "Our well is 50 meters deep," and they'd laugh. But they finally cut their tools down to small enough to go into engineering holes, and the dip meter gives you these little tadpoles give you the dip, and they give you the strike of clay beds. They're a micro-resistivity measurement down a hole, and then you can now correlate across these things looking at the shape of these channels. So this was a major advance to give us a sense that if we mine directionally, we will not be at risk by block slides. It'll tell us which facies are more controlled by critically oriented materials. Clearly, the strength of clays along these drapes were well understood at that time. This doesn't mean that we had no problems. Here you see a block slide occurring. Here's the clay drape almost losing the machine, undercutting the structure. These drag lines, by the way, were in their time the largest capacity drag lines in the world in terms of length of boom and the amount that they could pick up. There were bigger drag lines for just in terms of volume or mass in the cut, but the combination of the length of drag line and being able to make large bites was world setting. They were big machines. So there was an ongoing program, of course, of monitoring, inclinometers in the face, engineering geologists at the face. So there was an intense combination of all of the craft of the geotechnical observation method. But the dip meter that gave us insight into where we would be at risk because of these discontinuities was a major advance, and it's now used routinely. We actually had while we were draglining, some 42 block slides in the 29-year history of draglining. It came to an end. I'll speak to that in a moment. Of course, without losing a machine. And we learned, for example, how to characterize the displacement velocities on inclinometers that gave us enough time to walk machines out of harm's way. Under this environment, one learned with geotechnical insight, but also operational skill, to utilize drag lines smarter than we ever imagined would be possible when we proceeded with this technology. Now, the gas problem remained, And what happens when you have a gassy section, depending upon the richness of the feed, some will have more gas than others. The gas comes out of solution in the bitumen and causes the material to swell. You remember that's what gives us low strengths, and it swells closer to the face than it will back here, where it still stays into solution. And we get very substantial slope deformations when we mine through the gassy, more bitumen-rich material, which creates very substantial cracking up above, and we see situations like that, and we had to learn how to dragline mine through that sort of environment, also, of course, assisted by the observational method. We learned how to keep the dragline clearly away from this zone of extensive failure and how to approach the mining face in safe cutting modes and so forth. This shows you what happens in the rich material due to gas. This is material is flowing out and flowing out a significant distance under a kind of gas drive as the solution gas comes out of the bitumen. So the gas effects remain, but they're not dominating the advance of the mining. We learned then how to mine under all of these conditions. The draglines operated from June 1977 to March 16, 2006. They mined 2.2 billion tons of oil sand. They created 1.1 billion barrels of synthetic bitumen. They mined through hundreds of kilometers going back and forth of high wall. And we never lost a machine by virtue of the geotechnical contributions of the mining method. Had we been consistent with the original risk analysis, we would have lost 3 machines, 1 in 10 years. And we were about 30 years of dragline mining. And there was a remarkable evolution of risk management for the mining process tied to the kind of risk management system that we know so well in geotechnical engineering, the observational method. The draglines were replaced not because they're inefficient digging machines, but with the advance of very big truck capacity and big shovel capacity, the utilization of increasingly bigger trucks, now 400-ton trucks are the common carrying machine for ore and very big matched shovels, has a much better capacity for selective mining. Selective mining allows you to blend the ore, and that enhances production during the processing. The dragline is still a more, if you like, just production, would produce faster than the trucks, but doesn't allow that blending capacity. The investment in trucks is also more incremental from a capital perspective. You don't have to get all your capacity in the year 0. Let's turn to another part of the geotechnical challenge here, and that has to do with tailings at Syncrude. This is the photograph of its primary tailings dam during startup. It is some 18 kilometers around. It's not in the valley, it's on the flat ground. I calculated at least some years ago in terms of volume of constructed fill, the volume of material that is used to provide containment. It was at one time, maybe it is today, it doesn't matter. It's perhaps the largest earth structure by volume of engineered fill in the world. Built primarily after some starter dikes built of till, built totally out of sand with drainage control and so on. And it's now completed to its ultimate target, and tailings are being handled elsewhere. But it created its own interesting story of risk and reward in geotechnical engineering. We knew that the location being selected for this large structure was going to be a difficult foundation, because the overburdened materials above the ore are tills and sands, some outwash sands, but at this location primarily tills. And then there is a Cretaceous clay shale called the Clearwater Formation of CH deposit. Now, in our part of the world, whenever we see tills over clay shales, we think of glacial drag effects. So the deposition of tills in the terrain also produced shear on these Cretaceous clay shales and disrupted them and weakened them. Unfortunately, I don't have a picture. Sorry, this is a photograph. We'll come back to the Syncrude tailings pond, and we'll look at what's happening at this particular location, cell 23, which was a key learning point for us. But going back to the geometry, the nature of the ground, this is a photograph of an outcrop in a coal mine in the city near where I live. This is the Edmonton Formation, or some variant of it. It's also a Cretaceous deposit, and these are the coal beds, and you can see that the coal beds have been disrupted. Now, these deposits are actually absolutely horizontal in place. So this illustrates the kind of disruption and shearing that occurs with the process of glacial drag. So we're locating this Syncrude tailings dam on a clay shale of high plasticity, a CH material that has been subjected to glacial drag like this, and therefore we anticipate zones of weakness in the foundation. So that was known. It's very difficult to instrument in detail a structure 18 kilometers long. We had some zones where we thought the foundations were a little worse, some a little better. Some zones, because this isn't exactly a plane, that are a little higher, and here it's a little lower. There's more till in the location. So there are sentinel instrumentation placed every, I think it was perhaps 400 meters, inclinometers around to just get the first response to this structure as we began construction. And as we began construction, firstly at this location over several hundred meters and then at several other locations, we began to see movements, and we began to see the development of very high pore pressures, and we then began to flatten the original slope. But even after the slope was flattened to something like 8 to 9 to 1, which is getting fairly flat, we still began to get deformations. And here we'd put a few meters on, and here's an inclinometer at this location, and it's moving several centimeters at that location, less here and still contained in terms of a breakout zone. And every construction season, one would put a little more on, one get a little more slip, and so forth. And the question is this going to terminate, or is it going to take off? If it took off, many of us would have taken off. This illustrates a sequence. The construction of sand construction is by design in the summer only. In the winter, the sand comes out relatively warm from the process plant, and the steaming around it makes winter construction hazardous. You can do it, but you don't want to do it. So you'll see that there is a construction period, which one is placing material, and then no placement. So we've got the opportunity to see the slip that occurs, and then it settles down, slip that occurs, it's not settling down quite as quickly, slip that occurs, and so on. So this is the way the construction was proceeding. By this time, we had lots of instrumentation. And we had lots of pitsometers, and we had B bars of 0.8 and very high pore pressure response, and we had movements going on. And I can promise you, having worked through this, that we're at the limit of controlling the completion of this structure by means of limit equilibrium analysis alone. The ultimate, we had to adopt intense instrumentation in the breakout zone, make sure that the breakout zone was fully contained. By this time, we were getting fairly skilled in finite element analyses, and we were able to do some calculations for strains in the breakout zone. And to supplement the limitations of limit equilibrium analysis, we were working to tolerable strains in this potential breakout zone here. By the time this structure settled down, it had actually slipped some 55 or so centimeters. In final back analysis, after we had all this data, this actually was a slip of 50 centimeters with a factor of safety between 1.25 to 1.3, but the strains in the restraining zone were the basis of advising the owner that he could continue to construct, because there were, that was the major geotechnical input at that time. These circumstances, the strength, by the way, the average frictional resistance in this residual strength of this material is around 7.5 degrees. The pore pressures are very high, so basically one is trying to build a substantial embankment on a banana skin. And you can do it, but provided it's easier to build it if you have some breakout zone here that you can rely on. If the banana skin outcrops at the base of the structure, then clearly you're into building berms and you get diminishing return. We'd already flattened the slope significantly elsewhere in other parts of the structure. We had the opportunity to build some berms economically. These circumstances prevail. We have a large number of structures and various the development sites in which are on weak foundations, which are being managed the same way. Another geotechnical issue that developed in the early days of building the Suncord, first Tar Island Dyke, which was being built by sand, and one was learning to build sand, and one was then building the structure in order to stay ahead of this ever-increasing pond, was building it sufficiently quickly that static liquefaction of material was created, and you can see the outcome of that into the pond, the structure. It's an old photograph, I apologize for that. But so this was the learning that as one tried to build sand on uncompacted loose beaches, you're going to not get there. You're going to lose your structure, and part of that learning was transformed into learning how to build, get equipment out, and get compaction on the beach that you're going to going over. You might remember from the cross section that this structure builds in the upstream direction, so it's always building over previously placed beach. It's difficult to get equipment out all the way to build to compact that. So one has learned that as long as this beach is being placed above the water and you get significant downward seepage during the placement of the sand, you'll get to a dilatant mode. Sand deposited, what we call beach below water sand, is highly contractive, very liquefiable. Sand placed above will get dilatant if there's enough downward seepage, and therefore you've got to control the pond back here to get the downward seepage to avoid having to send equipment out to densify all of that. So these were some of the learnings related to static liquefaction. I think I mentioned, and I should repeat, this is not a very earthquake-prone area. The seismicity is low, so fortunately we don't have to pay attention to that particularly. You can't always control the rising ponds to ensure that you're building beach, so that you get downward flow and get enough densification. And sometimes one will end up having to build over with structure. This is the retention structure, build over material that is beach below water. In the late 80s with this particular dike, as I say, the beach above water could not be placed for various operational controls, and the beach below water was highly liquefiable, and one could fix that. One could say, well, let's do blasting, that's expensive, let's do vibrocompaction, that's pretty deep, and so forth. And those are always on our menu, so to speak. And it was thought that by building relatively slowly, inducing some shear by virtue of the way you're building into the beach below water material, you would get some densification, and that might make the material no longer so liquefiable. If that wasn't going to work, then one would have to, in this case, spend the money on blast densification. And you can see, if you have able to see this data, that data did move from highly liquefiable material here to material that densified under that extra loading. The gamble paid off. The N160s, in those days we didn't use cones to the degree we did, went from some 2 to 3 to some lower bound or lower 20 percentile, went from some 12 to 13, from 2 to 3 by this kind of loading. So that the geotechnical insights that might happen avoided, in this case, a very substantial densification problem, which we repeated more recently at one of the Syncrude operations called Aurora North. There, for various reasons of difficult pond control, they had lost the capacity to build beach. And the cones and SPT showed that if we're going to advance out over this, again, we're going to have very weak material and run the risk of static liquefaction. In this case, there was time to actually conduct a very substantial test fill. This is, I can't remember, 10 meters high or something like that, placed with characterization before, built in increments, characterization afterwards, and built again with characterization afterwards to say, yes, we will get from contractant to dilatant by construction alone and avoid the cost of a huge amount of blasting or a huge amount of perhaps loss of containment and other things that were the options of not achieving this. This shows some early data showing this is the contractant dilatant boundary that was guiding this work. These dots here are the dots from that past Suncor case history, and these are some average dots and converted into N160s. I'm sorry, this was standard penetration test. Most of the work was actually done with cones that I'll show in a moment, showing, again, the movement of material by virtue of loading with shear, but the shear from dead loading alone going from highly contractant out into dilatant. This illustrates the flood of data, in this case showing the kind of information from one lift to another lift, advancing further and further out from, in this case, a clean sand contractant boundary ratio that Peter Robertson, who's here, and Catherine Fear published some time ago, that we adopted as a reference base here. So you can see the data is advancing beyond that boundary. So that was another then example of the capacity of geotechnical engineering to contribute to the development of sand construction. And the issues of static liquefaction remain with us. Our primary trigger is foundation deformations that might move sufficiently quickly to trigger liquefaction. We've learned how to build slowly enough that building itself will not generate liquefaction. Well, that's going to be challenged in the next year as one sand dump, as it's going to be as opposed to a dam, will advance some 20 meters a year. And we'll see, fortunately it's going to be very flat so that the liquefaction issues are not going to be too severe. Let me turn to some construction-related matters. As I indicated, we operate in a cold environment, and there have been some major advances in cold region construction. This is a aerial picture of the Syncrude mine. This is the west side, this is the east side, well into its stage of development. This is in the early 90s, around 1992. And you can see that a road has been constructed across that mine. This is called the highway berm. This road was constructed to allow access while a highway was relocated on the other side of the mine. By conducting this berm, this extended the life of this mine by an additional 2 years. There was still ore there. They weren't finished mining. And this berm would allow us to store tailings in this region. The dike that you saw was full. We had to bring tailings into the mine, fluid tailings, I should add. And otherwise, if we couldn't get at that ore, they would have to open another mine, which is well north of this site, with a very large capital expansion. So this allowed a capital expenditure. This allowed the delay of the North Mine expansion by 2 years, and it also allowed additional testing of the process that we saw, hydrotransport, in which we fluidize the ore and pump it around for processing, both a major advance some 20 years ago now, and allowed the storage of tailings. So this structure had to be built under winter conditions and under the over some of that material that was dumped into the mine that you saw, and it had to be built to a dam specification. This was not just an advancing dump for access. It had to store fluids, and the fluids had to be built according to a dam spec. And later on, fluids come in here, and the fluids balance out. But for some years, those were the conditions of building this highway berm. The design was started in January 1992. We decided that we could do it, and so construction started in February 1992. The two were in parallel. You can often do that a lot easier in the mining industry. It was finished in August 1994. It was some 2.5 kilometers long. It's some 63 meters high. It involved 42 million cubic meters of fill on top of about 40 million cubic meters of mine waste, and there were pools to be drained and snow accumulation, and the foundation treatment was very challenging. And it had to function, as I say, as a retaining structure and constructed at temperatures down to minus 35 degrees. That led us to, here you see some of the foundation preparation of cleaning up and draining pools and doing some base preparation before the advance of the fill. And here you'll see advance of the fill even under winter conditions. We learned how to place material, and the requirement was to compact it before it froze. So one had these trucks coming in. There were typically 240-ton trucks in those days. They were loaded. They would place, and one had another truck nearby to make placement before it froze. So those were the conditions in which we were able to advance this fill under those conditions and meet the compaction spec, meet the zonation that would function as a dam, and it's performed extremely well since that time. So it's another outstanding example, I think, of risk and reward, tying the geotechnical capacity with the construction capacity in a mining environment, in this case, in which there were prizes to be achieved. The prizes here was the tailings management objective was achieved on time. We did bring tailings into that west side where fluid tailings are poured, and building this on time and on schedule with in the way I described allowed some 80 million extra barrels of oil to be recovered from the operation. Very substantial financial incentive, together with the learning curves for advancing other technologies. We're now, I guess, in stage 3. Since the original 2, we now have all the major companies around the world into the mining business. Shell is there in a big time, a large Canadian corporation. CNRL is there with a major mine. Exxon will start up later this year with a major mine, and others. And so the expansion of managing tailings has been a very challenging issue. You've seen that we've learned how to build sand dams. We've learned how to deal with weak foundations. A next major advance that I want to draw to your attention to is learning how to build with leaky foundations. This is just a snapshot of the Quaternary geology, and all of these sort of bullseyes and enclosed areas are sand channels. And I just don't expect you to read it. I just wanted to make the point that the Quaternary geology of the site is complicated. We've seen the complication that the glaciation, the tills advancing through the terrain have sheared a lot of the bedrock, the clay shale, and we've dealt with that. But we also have a substantial deposits of deep channels of sands and very substantial outwash deposits that vary from site to site. This results in what's called the Great Flood, the glacial Lake Agassiz down here, the burst, I can't remember how many, 10,000, 20,000 years ago, and large amounts of fluids and lots of dissection of the Quaternary created, rushed through here, making the geology on which we have to build these structures very complex. And this was first faced at the Suncor project, in which the tailings pond, that first tailings pond that we talked about, is actually here. in which its most southernmost tailings pond, these are all other tailing sites, in which its most southernmost pond is going to be built on exactly those conditions, exactly on these sandy deposits. Now, the industry operates under a zero discharge environment. There should be no discharge of process-affected water to the environment. So all these fluids that are going around and are generating some salts, and also have a material called naphthenic acid that's a product from processing the bitumen, have to be kept in storage at least until closure, and then we'll discuss what happens at that time, or at least it's a separate issue. So the issue then is dimensioning. That's an obvious design issue, but the issue is, what are we going to do to build a tailings pond now on clearly leaky geology in order to be consistent with the zero discharge requirement. This illustrates where the channels and outwash sands are. You can see a channel here going off into a major creek that goes out on the river. Here's another channel. Here's some outwash deposits that connect with channels. Fairly complicated geology. We do, I think, state-of-the-art geophysics with both land and air-based electrical resistance tomography to sort out the targets, with obviously a lot of drilling and hydrogeological characterization. And it's the hydrogeology here that's the heart of the containment issue. So this that illustrates a cave deposit that's a part of this structure, indicating some of the coarse materials that we're dealing with. I don't know whether... Yes, let me. This you perhaps won't see. Here's that one channel, and there's this other channel that goes out into the river and other outwash deposits here. So the containment here involves pumping well systems to cut off this channel, in which you create hydraulic closure by pumping to depress so that you don't have any water leaving the system going out into that channel. It involves slurry wall cutoffs here and here. There's passive relief wells because of the artesian conditions that develop around this dike with the porous foundation. And there's going to be a cutoff or pumping system as the fluids get up to that location. There isn't time to go into any details. In fact, we just completed a review board meeting last week, and I do believe that we've established the highest standards of hydraulic containment. We have monitoring wells, we have water chemistry being obtained all the time, and we can say that the process-affected water under this leaky foundation is fully contained using all of the tools of geotechnical engineering and hydrogeology. For those of you in the foundation world, there are foundation issues, but they're perhaps of a relative routine nature. I just want to illustrate that there are large piles to be dealt with. This indicates some of the Osterberg sort of load cell work that is done to do testing for pile design. Here's the installations, and here's some statnamic testing going on. And in the old days, the initial pile design, for these are sort of refinery type structures where we care about pile loading. In the old days, the allowable loads, there was a thinking because of the bitumen, we couldn't develop any significant skin friction on these piles, and the allowable loads from load tests done as base piles showed a fairly limited tolerance of load for design. More recent indications from more advanced testing has more or less doubled, if you will, the permissible load going into pile designs. So we can see that, again, geotechnical engineering is also making a contribution to more effective foundation design. I want to go on to one of the more exotic, and perhaps if you follow the literature on the oil sand industry, much criticized aspects in the technology that has to do with limited progress for reclamation and limited progress for closure. as I indicate, the landscape is full of waste after you've got these major mining situations. And the dry waste, the waste dumps and so on, can be reclaimed, they can be graded, they can be planted, they can be certified, which is our process of returning to the Crown. And we've gone through, there's a clear way forward to do that. It's the wetland forms in which we have all these accumulation of wet tailings that are more difficult. This illustrates one of the tailings dams, and this indicates an estimate that if all of the approvals that are related to the expansion of this mining industry are going to occur, we're going to have several hundred square kilometers of wet landscape, wet tailings to deal with. Now, this means that we're involved, partly in the dry and certainly in the wet, in one of the most challenging activities that combine hydraulics and combine geotechnical engineering to go from what we might call landscape engineering into ecosystem reconstruction as we bring this industry to closure. One of the interesting and challenging barriers to this are understanding the fine tailings. You might remember when they started this Suncor first tailings dam, they couldn't recover the water because it had a lot of fines in it. They had to keep storing it. The fines arise from the colloidal size, the clay content. There isn't a lot of clay, but there's enough clay that it affects the tailings. Moreover, in the extraction system, in order to enhance the recovery of bitumen, they use caustic, sodium hydroxide, which disperses the clays. And if any of you said, gee, why did I have to learn all that clay mineralogy or read all of that work in Jim Mitchell's book, this is a very good reason, because all of the answers to what happens are clear in the kind of understanding of the clays that we have. So we have highly dispersed, mainly kaolins, a little bit of smectite in it, highly dispersed by virtue of the process. And when these fines settle, as they do in the ponds, they actually develop a gel-like structure that is very, very slow to settle. But it does settle. It settles very slowly, and it settles without change of effective stress. So it hasn't read the concept of effective stress yet. It will get to a void ratio in time, perhaps a few hundred years, in which it'll understand the concept of effective stress, but it's still behaving in what is called in the chemical engineering world hindered settlement. It's still behaving as settling without change of effective stress. There's also some matters of toxicity, which we won't go into. If you could see this, you'd see these fine tails just being poured out of a beaker and behaving very fluid-like. So one of the challenges of reclamation is what are we going to do with this recalcitrant material that isn't settling and is consuming all its volume? In fact, we have perhaps 750 million cubic meters of it in storage so far, and it's growing every day. One of the thoughts emerging from research at our place was to sequester these fines instead of allowing them to come out of the sand and then consume all of this space we have, to convert the material from a segregating mixture when you deposit into a non-segregating mixture. And we thought that if we could add gypsum, for example, or lime, you can do other things, into the tailings, we could trap the fines inside. This illustrates, which we won't go into, a three-phase diagram that illustrates the conditions between fines content and water content and solids content, sand content, in which a material behaves sand-like down here, in which there is a boundary in which it segregates from a boundary that it doesn't. If you're able to look at it in detail, you'd see that changing the chemistry of the mixture will move the segregation boundary. Here then is a demonstration of what happens to these tailings when we add, in this case, gypsum into the material. These are large-scale field tests undertaken at Syncrude to deposit these materials at the base of the existing tailings dam. And this is what the material looks like. It's actually, it's not slurry-like. It actually has a consistency. It has a sand to fines ratio of something in the order of 4. It's releasing clear water, and it's not releasing fines. Moreover, it does know the concept of effective stress, and its behavior under sedimentation, under deposition, is forecastable and understandable, and will end up with a kind of reclaimable landscape. So we undertook large-scale field tests with that modified tailings. Several million cubic meters of material were placed at a commercial scale, and ended up with material that consolidated, in this case, for a limited depth, still some 12 meters depth, consolidated in about 6 months to something that is 83% solids, and which is then trafficable, and which is then cappable. One can actually get on the material with equipment, put clean sand on top of it, and cap it. So this is an example of the contributions emerging from geotechnical engineering to the wet side of the world, changing the behavior of tailings from something that is recalcitrant and not reclaimable to something that is reclaimable. And other solutions will undoubtedly emerge because there's a terrific amount of work looking into modifying the tailings behavior. If we go back to Tar Island Dyke, which was the first fluid tailings, we can see that it is no longer full of fluid. This was reclaimed last year, meeting the commitment of the corporation that it would be reclaimed by 2010. And you can see landscape performing. This was all green at the end of last autumn. However, it wasn't a clean reclamation. The actual reclamation was achieved by moving much of the fluid containment here to another deposit. Nevertheless, it was reclaimed. Here you can see the landscape engineering. You can see drainage being built. You can see terrain being created. All of this relates to understanding the settlement of the deposit as you build upon it, knowing where there might be some contaminant fluids and collecting them, and so forth. So there's a terrific interaction between landscape reconstruction and the geotechnical input into the deposit. And this is the Syncrude Pond, where that highway was built, which is now full of tailings. And you can see here landforms being created on the so-called CT tailings, because we need to have a little relief on that so that we get flushing of clean water into the sand to take some of the salty water out into capture ponds. So there's an interesting, if you will, new set of interactions between what we do geotechnically, what our hydraulic friends can contribute, and what we need to create a landscape that is transferable back to, in our case, the Crown, the government. So in conclusion, what I tried to do in this presentation, without getting into any equations, is to concentrate on the risk and reward achieved in the oil sands, not only through the production phase, but also as we're now entering the reclamation and closure phase. Geotechnical engineering has been an essential and creative participant in this vast and bold undertaking, and will remain integral in the success of the industry. I hope that you found the matter of some interest, and I thank you for your patience.
Well, we want to thank Dr. Morgenstern for this great presentation. There certainly were a lot of geotechnical challenges and so forth, but with ingenuity and great engineering, we can see that we can not only provide resources for us to use, but also to be able to reclaim the land and make it reusable again. So again, we want to thank you, Dr. Morgenstern, for this presentation. Let's welcome him again. Thank you.